There are 5 different types of reactions: synthesis, decomposition, single replacement, double replacement. The replacements can also be known as displacement. That's okay, means the same thing. And combustion. We're going to put off combustion for just a minute, okay? And we're going to look at single replacement, double replacement, synthesis, and decomposition. Anytime you start with one or with two, be it elements or compounds, and you form a compound, then that is a synthesis. For this top part, I'm using circles as elements and squares as compounds. So you can combine elements and elements to form compounds, but you can also combine compounds and elements to form another compound, or a compound and a compound to make another compound. Now, the difference between an element and a compound is an element has one capital letter. It represents one thing from the periodic table. A compound has 2 or more capital letters. Doesn't matter how many, just 2 or more. Now, decomposition is going to take a compound and split it up into elements or compounds. So here we have a compound, makes a compound and a compound. Here we have a compound that decomposes into 2 different elements. So it can go either way. And you can do compound into a compound and an element.
What is that? What's the reaction?
That's a decomposition. Okay. Single replacement and double replacement only deal with ionics. Okay, like ionic compounds. Got it? Single replacement and double replacement only deal with ionic compounds. Ionic compounds always have a cation and an anion. The cation is the metal, the anion is the nonmetal, or sometimes the polyatomic. Right? Okay, so I'm going to use the same color coding system that I used last unit, where my cations are blue and my anions are green.
Correct.
And I'm going to color code this, okay? So cations are blue, metals are cations. Hydrogen is not a metal, but it has the 1+ charge.
Is that the double replacement?
This is the single replacement. Now, I told you before that single replacement reactions are like a third wheel on a date that ends up stealing the date. So what you'll notice is that there are either 2 cations and the anion switches, or down here there's 2 anions right here, there's two anions, and the cation switches. Yes.
Is that why that one's green, the rest are blue?
Correct. Blue are the cations, green are the anions.
Then I'm like, what about like the last one?
The last one, chlorine is an anion, bromine is an anion. Sodium is a metal, so it's a cation. So it switched from bromine to chlorine and made NaCl. And now bromine's all by itself.
Porker, I mean. So cations. Wait. Which ones are blue? Which ones are green? Cations.
Blue are cations, green are anions. Okay, so what's important to notice in the single replacement is that you have two of one type of ion and one of another, and it's going to switch. Okay? Now, for the double replacement, you are always going to have two cations and two anions, and you're going to switch. It doesn't matter if you look at it as switching cations or if you look at it as switching anions. You're just making new couples, okay? So for this, like, I'm not going to do every example, but these are our cations. Whoops. And these are our anions. And notice how they switched places. We're going to get to a point in the unit where we're going to predict products of single replacement and double replacement reactions. And this is like the reason that I spent so much time with ionic bonding and color coding and making sure that you saw the pattern and knowing that there's always two parts to an ionic bond, a cation and an anion, is because when we do these reactions, if you can identify the cation and the anions, then you can see the pattern and switch them. Does that make sense? A little bit? Okay. Dissolved, now the chemical symbols, there's a state of matter next to every compound. If there's a G, it's a gas. That's obvious. If it's an S, it's a solid. If it's an L, it's a liquid. I write my L's like that so that they look like not ones. Okay? Dissolved in water, okay? There is a difference between salt water and liquid salt, okay? Like, or liquid sugar. Like, okay, caramel, technically, like, to make caramel, you make sugar a liquid. Like, you boil
So
sugar.
are you saying like, because you're saying like salt water, like, you know, like salt water, like the ocean, it's like not all salt.
Correct, it's water with salt in it.
And like pure salt, like water would just be like everything is like salt.
So if we think of syrup, like, maple syrup obviously is not just plain sugar, but go with me on the analogy. If you have maple syrup, then that is like liquid sugar. Are you with me?
Yes.
Whereas
like fudge.
sweet tea is sugar in water. Okay? That's the difference between AQ, which stands for aqueous. We're still recording. You can be team aqueous or you can be team aqueous. I don't care. And that means dissolved in water, which is different than being a liquid. Got it? Okay, sets of reactions. that typically involve solids or gases are going to be, or no, ions in solution are going to be your single replacement and your double replacement. Because notice how they all have AQs in every single reaction. There's some AQs here, but in every single replacement, double replacement, there is an aqueous. Okay? So this is going to be C and D. Based on the examples provided, which sets of reaction in Model 1 typically involve gases or solids, A and B are really, really predominant with the gases and the solids. Whoops. But there's still some in all of them. So if you're talking about where are solids and gases, they're in all of them, but mostly A and B. Okay?